So today I'll be talking about limits and continuity. So let's take a polynomial for example. Let's say we're graphing a set of axes like this. Okay, let's say we had the function y equals x cubed. Okay, so that's going to look something like this. Okay, so let's say we were trying to figure out the value of y when x was equal to 3. Okay, so if x was 3, we'd go straight up and we'd get our corresponding y value. So to figure out what y is, we would just put in 3 for x, so 3 to the third, that's going to be 27. So even though I didn't draw it to scale, the y value is 27 when x is 3 for the graph y equals x cubed. So polynomials are known for being continuous. And they're continuous because no matter how far we go to the left, and no matter how far we go to the right, it doesn't matter what your x value is, you're always going to get some value for y. So it continues the entire way. Its domain is infinite, from negative infinity to positive infinity. Okay, so polynomials are always continuous. So taking the limits of polynomials, that's just going to be the polynomial evaluated at some value x. Okay, but what is a limit? Well, let's take the same function, y equals x cubed. Okay, so we got our axes here. We got our graph of x cubed. Okay, let's say we were trying to find the limit, and we'll just call it f of x. So f of x is x cubed as x approaches a value a. Okay, so that's going to equal L, our limit. Okay, so let's say we're trying to find the limit as x approaches 3, like we did above. So the limit as x approaches 3 of f of x, what does that equal? Well, the limit is just what the function approaches, the value of the function approaches as x approaches some value. Okay, so let's say we split it into 1, 2, 3, and 4. Okay, so y equals x cubed, the function starts at y equals 0 when x equals 0. As it kind of nudges closer to x equals 1, it's going to go up in value. So a nudge to the right means it's nudging upwards in the y direction. So as x approaches 1, y is also going to approach 1 because 1 cubed is just 1. Okay, what if we're trying to find the limit as x approaches 2? Well, as we move closer and closer to 2 from either directions, right? If we're moving from left to right, the function is going to nudge up. And if we're moving from right to left, the function is going to nudge down towards some value. And that value right here, that's just going to be the function evaluated at x equals 2. Okay, and it's the exact same thing if we're evaluating the limit. Oh, whoops. If we're evaluating the limit at, just redraw it here, at x equals 3. So if we want to find the limit of the function at x equals 3, I'll just kind of draw it a little bigger here. Evaluating the limit at x equals 3, we're going to see what the function kind of nudges closer to as we nudge towards 3 in the x direction from either the left and the right. So what value does the function approach as we move towards x equals 3? Well, it's just going to be 27 like we found before because we just plug in 3 for x, we cube it, and we get 27. Okay, so our answer for the limit of f of x as x approaches 3, that's going to be the function evaluated at 3, which is just 27. But since polynomials are continuous, evaluating their limits is super easy. Okay, so it's just like finding the value of the function at x equals 3. Okay, but what if we had f of x equals x squared minus 1 over x minus 1? Find the limit of f of x as x approaches 1. So this one you might be thinking, well, this is a rational expression, so let's just try plugging in 1 for x and see what we get. Okay, well, if we plug in 1 for x, we're going to get 1 squared minus 1, so that's 0, over 1 minus 1. So we're going to get 0 over 0. Some people might think that this is 0, but anytime we divide anything by 0, that's going to be an infinite, a non-real answer, right? So this is undefined. Okay, so plugging in 1 for x isn't going to work. You're not going to be able to evaluate every limit just by plugging in the x value that it approaches. Okay, so let's draw this out. How would this look if we were to draw it out? Well, first, in order to kind of graph it, we should probably factor the top and the bottom. So this is a difference of squares. Okay, so if we factor x squared minus 1, it's going to be x plus 1 times x minus 1, right? We see an x minus 1 on the top and bottom, so we're just going to get x plus 1. So the function doesn't equal x plus 1, but it closely resembles it, and it has a point of discontinuity at x equals negative 1. Okay, so if we were to graph it, we would treat it like x plus 1. So x plus 1 would have a y-intercept of 1 and a slope of 1. So this would be 1 right here, except there's going to be, that's actually not true here. So at x equals 1, there's going to be a hole. Okay, so it's going to look like x plus 1, where 1 is the y-intercept, except right here, there's that point of discontinuity, the hole in the graph. Because if we were to plug in 1 for x, we would get an infinite answer. So the function doesn't exist when x equals 1. Okay, but even though the function doesn't exist where x equals 1, we can find the limit of this function as it approaches x equals 1. Okay, so what value does this function get closer and closer to as we move towards x equals 1? Well, we can figure that out by just treating this like it's x plus 1. Okay, so if we just pretend y equals x plus 1, we can just plug in 1 for x, and we're going to get 2. So as x approaches 1, y is going to approach 2. So as we nudge closer and closer to 1 in the x direction, we're going to nudge closer and closer to 2 in the y direction. So the limit is going to equal 2. Okay, let's talk about a different type of discontinuity. Let's say we had a function g of x, and let's say it was a piecewise function. So piecewise function just means we're kind of splitting it into two parts, x squared minus 1 over x minus 1. So that's the same thing we just had. Okay, and obviously we know x can't equal 1 for this function. And let's say when x is 1, the y value, or sorry, the g value is going to be 1. So what this means is we're going to graph it the same way. Okay, we're going to graph it the same way. So we know there's going to be that point of discontinuity. So when x is 1, there's going to be a hole. Because this part even says right here, x can equal 1. But when x does equal 1, we're saying that the value of the function is going to equal 1 as well. So this is 2, this is going to be 1, where the y-intercept is. It's kind of going to jump down to x equals 1. So this is what the piecewise function would look like. And this is called a jump discontinuity. So see how the limit, all right, the limit of g of x as x approaches 1, it's always going to equal 2, except f of 1, or it's not f, it's g of 1 equals 1. So see how these don't match? that means that it's not continuous at that point. Okay, so the function doesn't exist at x equals 1 if we didn't have this piecewise function g of 1, or this piecewise function where y or g equals 1 when x equals 1. So that's called a jump discontinuity, when there's a hole in the graph and it kind of jumps down, or maybe it jumps up here to another point to make it defined at that x value. Okay. So that's a jump discontinuity, or sorry, this is a removable discontinuity. Pardon me, a removable discontinuity, because we can remove the discontinuity by just putting a point into the hole, and it's also called a point discontinuity sometimes. Meanwhile, a removable I'm getting my discontinuities all mixed up. Your jump discontinuity would be if we had a function. Let's say it looks like this, right? And there's a hole right here, and it jumped down, straight down from that x value to a new y value and kind of continued on. So this is a jump discontinuity because it's continuous going to the left, but coming from the left to the right, once we hit this x value, let's call it like 1, once x equals 1, it jumps straight down to a new y value and kind of continues on to the right. So that is a jump discontinuity. There's also a different type of continuity called an infinite discontinuity. So a popular one is y equals 1 over x. There's a vertical asymptote, some of you might remember, when x equals 0. Okay, so if we were to graph this, it was kind of that funky looking graph where we knew there was an asymptote at x equals 0. Okay, and it's going to look like this. Okay, so it kind of goes in all directions. When x equals 0, it goes up to infinity coming from the right, from the positive x, and it goes down to negative infinity coming from the negative x, from the left. Okay, so this is called an infinite discontinuity, which just means it goes up to infinity, down to infinity at the same x value. And there's one more I'm just going to go over quickly here. It's called an oscillating discontinuity. Okay, so a super common one that we see lots of the time in calculus is y equals sine x over x. Okay, so what this graph is going to look like is this. So it's going to kind of oscillate back and forth. I'll draw it a bit better. So it's going to kind of flatten out and get bigger once we come here, and kind of come upwards, come back down, and flatten out once again. Okay, so it's kind of a weird looking graph. How can we figure out the limit? Let's say we want to figure out the limit as x approaches 0 of y. Okay, once again, we can't just plug in 0 for x, because since x is the only thing in our denominator, it'll just be sine of 0, right, which is just 0 divided by 0. So we end up getting 0 over 0 again, which that's not something that we can evaluate. We can't say it's 1 just because it's the same thing over itself. We can't say it's infinite because it's not. We know this isn't like infinity right here. So how can we evaluate this using our calculators or algebraically? Well, we can't do it algebraically, but let's just kind of look at our calculators. So let's say we were starting at x was negative 0.1. Okay, so if we plugged in negative 0.1 for x, we would get sine negative 0.1 divided by 0.1. Or sorry, divided by negative 0.1. So if you put that in your calculator, okay, so we're going to do sine of negative 0.1. So that's about negative 0.1 divided by negative 0.1. Okay, so the answer we get is 0.0 9983. So that is pretty darn close to 1. Okay, let's do it from the right side now. So y equals sine x over x. Let's say x was 0.1 now. So now we're starting at positive 0.1, and we're kind of sandwiching x equals 0. So we're going just to the left and just to the right of it. Okay, so we're going to go sine of 0.1 over 0.1. Okay, so sine of 0.1, that's going to be basically 0.1 divided by 0.1. That's also going to be 0.9983. Okay, let's get even closer. Let's go sine of negative 0.01. Okay, so that's going to equal negative 0.0099998333. Let's divide that by let's divide it by negative 0.01. So when x is negative 0.01, y is going to be 0.999983. So you can see, as we get closer and closer to 0, as we nudge closer to 0, the y value is going to approach 1. It's close enough to 1 that we can just say it's 1. So the limit of y as x approaches 0, that's going to be 1. So even though we can't plug in 0 directly into this equation, we can look at our calculator and figure out kind of what the function is heading towards as we head towards x equals 0. Okay, so that's a pretty common limit that comes up quite frequently. All right, so let's just kind of solve some, let's go through some questions that are asking about limits here. Okay, so let's do some worked examples. Let's see, what are some good ones we can go over? Let's evaluate the limit as x approaches infinity of 2, or no, let's go 6 sine x, or yeah, we'll go 6 sine x plus 5x over x. Okay, so one property of limits is that we can split this into the sum of limits. Okay, so if we split this into two fractions, this would be the limit as x approaches infinity of 6 sine x over x plus 5x over x. Okay, so if we're summing two functions together, we can just split that into two limits. So if we bring the constant out front, right, if we bring that out front, this is going to be 6 times the limit as x approaches infinity of sine x over x, plus there's a 5 here in the constant, so we can go plus 5 times the limit as x approaches infinity of x over x. Okay, so sine x over x, we just went over that one, right? So remember, it was an oscillating discontinuity, and it had a horizontal asymptote, right? It kind of looks like this. So as x approached positive infinity, it kind of flattened out, and we could see that the limit as x approached infinity was going to be 0. Okay, so all this is 6 times 0, because the limit as x got closer and closer to infinity of sine x over x, that was 0. Plus x over x is just 1. Okay, so we can simplify that to 5 times 1. So that limit there is going to be 5. Okay. What's another one that we can go over? Let's say, okay, let's do the limit as x approaches 1 of x to the 4th plus x squared minus 1 over x squared plus 5. Okay, so all we need to do for this one, if we plug in 1 for x, the bottom isn't going to equal 0. So we can just substitute this in and find the value of the function. Find the value of the function at x equals 1. So we're not going to have to do any algebraic manipulation. All we do is we plug in 1 for x. So 1 to the 4th plus 1 squared minus 1 over 1 squared plus 5. So 1 to the 4th is 1 plus 1 squared is 2 minus 1 is 1 over 1 squared plus, so that's 1/6. Okay, so if we were to graph this function, if we were to get closer and closer to x equals 1 from the left and from the right, the function's value would approach 1/6. So that's about 0.17. Okay. Let's go one more here. Okay, let's do just trying to find a good one we can go over here. Okay, let's do the limit as x approaches -2 of 1 over x plus a half divided by x plus 2. So this isn't one that we can just substitute x in for, right? Or substitute, x equals -2, because if we put in -2 for x, that'll be -2 plus 2, which will be 0 on the denominator. So anytime we substitute x in there and we get 0 on the bottom, we're not going to be able to solve it just with plugging in, with substituting the x. So we're going to have to do some algebraic manipulation. Let's combine the top fractions here. So in order to combine them, we have to make the denominators the same. Okay, so if we multiply this by 2 over 2 and multiply this by x over x, both the denominators are going to be 2x. So this will be the limit as x approaches -2 of 2 over 2x, or already a bit higher, 2 over 2x plus x over 2x divided by x plus 2. So on the top, this is going to be the limit x approaches -2 of 2 plus x over 2x divided by x plus 2. Okay, so 2 plus x and x plus 2, the order in which we add two things together doesn't matter. So 2 plus x and x plus 2 is the same thing. If we have 2 plus x over 2x and we're dividing by x plus 2, those two things are going to cancel out, and we're just going to have the limit of 1 over 2x as x approaches -2. So as much as we can, we want to simplify this as much as we can. So now we have it just 1 over 2x, and if we plug in -2 for x now, we're not going to have 0 on the bottom. So it's going to be 1 over 2 times -2, which is just -1 over 4. Okay, so if we didn't do this manipulation of the fractions, we wouldn't be able to solve this problem because we couldn't just plug in -2 for x. Okay, so just some things that I want to go over in terms of properties of limits. Okay, I kind of did some of them in the examples, but the major properties that I want to go over is that if we are taking the limit of a function as x approaches a is typically the letter that we use to represent like what it's approaching. If we're taking the limit of the sum of two functions, so I'll just call them f of x and g of x, that's going to equal the limit as x approaches a of the first function, so f of x. This is going to be some number plus the limit as x approaches a of g of x. So the limit of two functions added together is just the sum of their individual limits. Okay, so that can kind of be helpful when you're doing certain questions. Similarly, if this was a minus sign, it's the exact same thing. So if we were doing minus g of x, it would be the same thing minus the limit of g of x. Okay, two more properties I want to go over. Limit as x approaches a. Let's say we're finding the product of two functions, so f of x times g of x. That's going to be the limit as x approaches a of f of x. That's going to be some number times the limit as x approaches a of g of x. So the limit of two products is just the product of the two limits. So if we're trying to find the limit as x kind of nudges towards a of two functions being multiplied together, maybe it was like x times sine of x. We would call this x our f of x, the sine of x our g of x. We would find the limit as x approaches a of x, and we'd multiply that by the limit as x approaches a of sine of x. Okay, and lastly, okay, just kind of the quotient rule. All kind of the same idea. If we're dividing two fractions, finding the limit of this function here, we call it h of x. That's going to equal the quotient of their individual limits. So it's going to equal the limit of f of x as x approaches a divided by the limit of g of x as x approaches a. So nothing too crazy, just some properties that we can kind of use to our advantage when we're solving these types of questions. So to kind of recap, there's four main different types of discontinuity. So this is called a removable discontinuity because we can remove it by just kind of plugging in that point. Also referred to as a point discontinuity. This is a jump discontinuity because we're jumping down from one point to another, from one hole to a point that actually exists within the function's domain. Okay, this is called an infinite discontinuity because as we're approaching some asymptote, some x value, it splits off into positive infinity and negative infinity, right? That's an infinite discontinuity, and this is called an oscillating discontinuity because it kind of oscillates towards one asymptote. And sine x over x is a super common one, and we can kind of numerically analyze this by using our calculator and seeing what the function approaches as we approach some x value. So we just went through some questions here, and yeah, that's kind of the main idea with limits. So in the next video, we're going to use limits to figure out the definition of the derivative, and I'll talk about that later. But derivatives, that's just finding the slope of the tangent line at some point on a curve. Okay, so we can actually use limits to figure out derivatives, which is kind of cool. So I'll see you in that video.